Welcome, students, to today's Explainer. Get ready, because today we're going to unravel a really fascinating ecological mystery. We are going to explore how the fundamental chemical elements of our planet relentlessly cycle through the world around us. And interestingly enough, we'll see how sometimes that very same natural cycle can bring dangerous toxins right to our dinner plates.
Okay, let's dive right into this. It sounds kind of like a riddle, right? How exactly does a microscopic piece of plankton just floating around in a bay connect to the safety of the fish you might be eating for dinner tonight? Well, to answer that, we've got to take a journey from the absolute most basic microscopic elements of matter all the way up to real-world global ecological impacts.
Here is our roadmap for today's lecture. First, the foundation, elements of organic molecules. Second, the nitrogen pathway, air to soil. And finally, the toxin trap, biomagnification.
Let's start with part 1, the foundation, elements of organic molecules.
If we strip life all the way down to its basic chemical building blocks, we find there are 6 essential elements that make up our organic molecules. We've got carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. Now, what's genuinely amazing about these 6 elements is that they don't just appear out of nowhere. No, they are strictly conserved and constantly recycled throughout the entire biosphere.
And that brings us to a really critical definition, so definitely jot this down for your notes. Because geology, chemistry, and biology are all working together to move these 6 elements around our planet, we call this process a biogeochemical cycle. It makes sense when you break it down. Bio for the living organisms, geo for the rocks, soil, and water, and chemical for all those molecular transformations taking place.
So the absolutely crucial point here is the distinction between energy and matter. Energy flows directionally through an ecosystem. It comes in as sunlight, gets used by plants, passes up the food chain, and ultimately leaves the system as heat, right? It's a one-way street. Matter, on the other hand, the actual physical atoms of carbon, nitrogen, and the rest, is conserved. Think about this. The atoms inside your body right now have existed for billions of years. They have been endlessly reused by the Earth's biogeochemical cycles. How wild is that?
Okay, moving on to part 2, the nitrogen pathway, air to soil. Let's see how atmospheric nitrogen actually makes its journey into the food web. Here's a surprising fact for you. Nitrogen gas actually makes up roughly 78% of the air we breathe. Literally, we are swimming in it right now. But there's a major catch. This atmospheric nitrogen exists as a super tightly bonded molecule, N2. Plants and animals just cannot use it in this gaseous form. It's kind of like dying of thirst while floating in the middle of the ocean. The resource is absolutely everywhere, but you just can't process it. So to actually get that nitrogen into the living world, we have to rely on a step-by-step biological process. And this is powered almost entirely by microscopic bacteria. The first crucial step is nitrogen fixation. This is where specialized bacteria grab that stubborn atmospheric gas and convert it into usable organic compounds. Next up is ammonification. Here, different bacteria and fungi step in to convert nitrogenous waste from dead animals back into ammonium in the soil. Step 3 is nitrification, which converts that soil ammonium into nitrites and nitrates. And finally, we have denitrification. This is where yet another group of bacteria converts those nitrates right back into nitrogen gas, sending it up to the sky and completing the whole cycle.
Now notice how visually interconnected this cycle really is. Trace the path with me. From atmospheric nitrogen coming down into the terrestrial food webs and going straight into the root nodules of legumes, so think peas and beans. Symbiotic bacteria, like rhizobium, live right inside those roots. They pull the nitrogen directly into the plant, which then gets eaten by consumers, passing that nitrogen all the way up the food chain.
But this beautifully balanced natural cycle is currently facing some massive human disruption. See, when we use artificial fertilizers in agriculture, we're basically dumping vast amounts of excess nitrogen and phosphorus onto the land. And when it rains, all that surface runoff washes directly into our lakes and rivers. This kicks off the devastating process called eutrophication. It causes this explosive, totally excessive growth of microorganisms that rapidly depletes the water's dissolved oxygen. It literally suffocates and kills off the ecosystem's fauna.
Take a look at these red circles, which map out global dead zones. Notice the massive concentration of them along the coastlines of highly populated areas. I want to draw your attention specifically to the United States here. Right down in the Gulf of Mexico, fertilizer runoff funneling all the way down the Mississippi River Basin has created a staggering dead zone spanning over 8,463 square miles. That is just
entire aquatic ecosystems completely wiped out of their normal flora and fauna.
Which brings us to Part 3, the toxin trap, biomagnification.
Let's look at the dark side of these elemental cycles. Please jot down this definition for biomagnification. It's the increasing concentration of persistent, toxic substances in organisms at each successive trophic level. Remember earlier when we said matter is conserved? Well, when a primary consumer eats a primary producer, it takes on its matter. But if that producer absorbed a heavy metal or some toxic chemical that doesn't easily break down, that toxin gets passed along. It gets trapped inside the consumer's biology, and it becomes highly concentrated the higher up the food chain you go. To put this into perspective, a NOAA study in the Saginaw Bay of Lake Huron tracked toxic chemicals called PCBs. If you check out the x-axis at the bottom, that tracks the enrichment of nitrogen isotopes. Biologists actually use that as a marker for a creature's trophic level. Watch what happens as we move from the bottom left to the top right, climbing higher up the food chain. That blue line, which is tracking the PCB toxicity, climbs steadily upward right along with it.
Let's contrast the two extremes on that chart. Down at the very bottom of the food web, the primary producers, the phytoplankton, have a relatively low level of PCBs. But as the zebra mussels eat the plankton, and the small fish eat those mussels, and the large fish eat the small fish, the toxin magnifies. By the time you reach the apex consumer of that ecosystem, the walleye, you are looking at more than 4 times the amount of PCBs compared to the phytoplankton. The dynamics of the ecosystem literally amplify the danger.
And listen, this isn't just an abstract concept about fish in a distant lake. This directly impacts what you buy at the grocery store. Because of biomagnification, heavy metals like mercury heavily accumulate in top-tier ocean predators. This is exactly why the EPA issues strict warnings that pregnant women and young children should entirely avoid eating apex consumer seafood, things like swordfish and shark. Instead, they recommend lower trophic fish like salmon or tilapia.
So we return right back to where we started. The elements of life are a closed loop. They are endlessly cycling through the air, the soil, the water, and our very own bodies. But as we've just seen with agricultural runoff and toxic biomagnification, we are no longer just participants in this cycle anymore. We are actively altering it. I'll leave you with this final thought for today's lecture. If our daily actions can rewrite these fundamental cycles of life, how will our current disruptions alter the future of our food web? Thank you for joining me for this explainer, students. Keep questioning the world around you.